Hey everyone, Mr. Fritz here. We're going to talk about lines in space in this video. And really this is a whole lot like talking about lines on a plane that we've done before, making these vector equations, but we're just going to add a third component, the z component, or the k unit vector component. So let's just talk about some stuff here. Let's actually begin with what the original, or what the general equation of a vector equation is in 3 space. So the vector equation x, y, z, the position vector for any given time t is going to equal some a1, a1, try that again, a1, a2, a3, plus some scalar t times b1, b2, b3. This is just like the r, vector r, position vector r equals some initial position, not always initial position, but some position vector a plus some scalar t times some directional vector or velocity vector b. So this is just like what we've seen before. Let's kind of translate all of these things to parametrics. So if I'm looking at the parametrics, I'm just splitting out my x, my y, my z of all 3 of these pieces in my vectors. So the parametric equation x is going to equal a1 plus b1t. The y component is going to equal a2 plus b2t, and the z component is going to equal a3 plus b3t. Basically what parametrics are doing is they're just segmenting out the 3 components of my vector equation. We like vector equations because it kind of puts all of the stuff together, and why we might like parametrics is because it can separate things out. Sometimes they have advantages and disadvantages. In general, lines in space, this t is not always going to represent time. And so even though we talk about the initial position, really sometimes this is not just an initial position, but it's just like any position or any point on the line. It doesn't have to be the initial position, sometimes it is. But hopefully you're seeing that that's coming from this vector with all the a's. This is your a1, your a2, and your a3, some point on the line. And then the direction vector, we've called this velocity vector in the past. Doesn't always have to be velocity. It could just be the general direction of some object. And that's given by b1, b2, b3 in this vector equation. So kind of all 3 of these things, or all 4 of these things kind of all work together and moving forward. So now we can draw these lines in space that are not just 2 dimensions, x and y, but they can actually come out of this plane as well in 3 space. So let's see an example of just writing a line, the equation of a line in 3 space. We want to find the vector equation and parametric equations of the line through this right here. This is my point, 1, negative 2, 3, and in this direction, 4i plus 5j minus 6k. This is my direction. So let's first do the vector equation. Vector equation, x, y, z, the position vector is going to be given as my point 1, negative 2, 3, plus some scalar t times 4, 5, negative 6. Yes, that's it. This could have been a t, could have been an s, really doesn't matter. It's just some scalar value. And then so now let's do parametrics in another color. Let's make that purple. Here's my parametrics. And I'm just segmenting out all of these components from my vector equation. So x is going to equal 1 plus 4t, or you can write this as 4t plus 1, either or. Y equals negative 2 plus 5t, and then z is going to equal 3 minus 6t. That's it. Writing the 3 equations is just as simple as taking the components out of your vector equation. So here's an example I'd like you to try. Oop, those are the answers. Take a look at the answers. Well, you've already seen it. Here are the answers to your you try too, but maybe cover these up or pause the video, take a look at your notes, and see if you can't come up with these equations for these, and then take a look at these answers I've given you. I'm pretty sure that I've posted the answers on the next slide as well. So once you finish these 3, these are finding vector equations. I think in the next example, the you try 3, I want you to find parametric equations. So give those a shot, pause the video, and come back once you've finished all of these U-try problems, U-try 2 and U-try 3. And here are my answers to U-try 3. I think the trickiest thing about this is the example, or the letter C here. This is perpendicular to, now what's like this XOY thing? Well, if we think about what's going on, we have the XY plane, and we have the Z axis running through this. So this is what makes this thing in 3 dimensions. And this O is typically what we call the origin O. So we have to describe a plane by 3 points. So XOY would kind of be what the 2-dimensional plane is, which is flat on the screen, and Z is coming out of it. If I am perpendicular, here's my visual aid. Here's like my XY plane. So it's a flat surface. This is my plane. If I'm perpendicular to this plane, I can't be moving in this plane. Otherwise, I'm not perpendicular to it. I'm still moving in some XY direction. So the only way I can be perpendicular to a plane is if I'm coming directly out of it. So here's my plane, and I have to come out of that plane. This is why in this U-try example 3, you'll see that there's no t on the x, no t on the y, but there is a t on the z parametric equation because I'm coming out of that plane but not moving up or down, left or right at all. Does this have to be a 1t? No, it could be a 2t, a 3t, a negative 20t. Anything, any t direction or any direction in the z direction is fine. It will be perpendicular to this one here. So hopefully that makes a little bit of sense. In the next video, we're going to talk a little bit about, what are we going to talk about in the next video? Line classification. So we've got one more for these video notes, and I'll see you in the next video.